let's say we have a subset y of the space a to the n, of the affine n space. Then we want to prove the following statement, that z of I of y is equal to the closure of y. You can find this statement as a part of proposition 1.2 in Hartshorn's book in chapter 1. And, well, we're basically going to go through his proof, through Hartshorn's proof, I mean. So, proof. Well, first of all, note that y is in z of I of y. This is basically by definition, because I of y is the ideal that vanishes on y, and z of I of y is the common zero set of this ideal. And since I is made up of polynomials that vanish out of I on I, of course y is in the common zero set of these polynomials. So we have this inclusion. And now this set here is closed. So we have a closed set containing y. And remember, the closure is the intersection of all closed sets containing y. So, so since we have a closed set containing y, we have also that the closure is inside the set z of I of y. So we have this inclusion. And now what we really need to prove is the other inclusion. So we need to prove that z of I of y is a subset of the closure. To do this, we assume that we have a closed set V. So, I'm sorry, W. A closed set W. And the closed sets in the Zariski topology, of course, by definition, zero sets of ideals. So we can write this closed set W as the zero set of an ideal A. So this is the same as, and now we assume that W contains y, and by what we have just said, we know that this is the same as z of A contains y. And this means that I of z of A is a subset of I of y, because this map I is inclusion reversing. So if z of A is a subset of y, then I of z of A is a subset of I of y. But we also have A is a subset of I of Z of A. So if we now apply the function Z on this, we have Z of A contains Z of I of Z of A, and remember up here we said that I of Z of A is a subset of I of Y, so this now under this inclusion reversing map Z translates to Z of I of Z of A being a subset of Z of I of Y. So remember this one here, this is V, I'm sorry, W. This is W. So we have that every closed subset that contains Y contains Z of I of Y, which is also a closed subset. And this, of course, means that Z of I of Y is nothing but the closure of Y. And this concludes the proof.